shielding effect is the attraction between an electron and the nucleus in any atom with more than one electron shell. It describes the balance between the pull of the protons on valence electrons and the repulsion forces from the inner electrons. So these electrons are constantly trying to get to the nucleus. They're being pulled in by the nucleus, but they're at the same time the innermost shell of electrons are pushing it out due to the negative on negative charge. That's basically the shielding effect. It explains why valence shell electrons are more easily removed from the atom, as well as atomic size. The more shielding, the further the valence electron can spread out and bigger atoms will be. In addition, it can equate the effective nuclear charge. The effective nuclear charge is the net positive charge experienced by valence electrons. It can be approximated or equated with the formula right here, where Z minus S. Z is the atomic number and S is the number of shielding electrons.
This is the electronegativity model. Electronegativity is a measure of the tendency of an atom to attract a bonding pair of electrons. Fluorine, the most electronegative element, is assigned a value of 4.0. Values can go down to 0.7. An atom's electronegativity is affected by both its atomic number and the distance at which its valence electrons reside from the charged nucleus. The higher the associated electronegativity number, the more an element of compound attracts electrons towards it. Atoms that have high electrons will attract more electrons and sometimes steal from other atoms. Atoms with low electrons will share with other electrons and sometimes losing some.
This is the ionization model. Ionization energy is the energy required to remove an electron from a neutral atom in its gaseous phase. Ionization is the opposite of electronegativity. Elements on the right side are normally have a higher ionization energy, and those are nonmetals and noble gases because their valence shell is almost filled. Ionization energy within a period normally increases from left to right due to valence shell stability. Ionization energy of the elements within a group normally decreases from top to bottom. This is due to electron shielding.
Okay. My project, 3D project, is on the periodic trends in metallic character. The orange, red, and pink down here are metals. The pink going down like a staircase is the metalloids, and the yellow is the nonmetals. Metallic character is a degree of metal character of an element. It is similar to the trend for atomic radius. The arrows represent if you go from right to left, the metallic character increases, and if you go from top to bottom, it increases as well. And if you look at it from down here, it shows the columns and heights of increases. Metallic character also includes the ability to be reduced, formation, and also the formation of ionic chlorides and basic oxides, and also the ability to displace hydrogen from dilute acids. So, yep, metallic character increases that way, it increases downward, or you could go decreases from left to right, or decreases from bottom to top. But either way, it's larger here and smaller on this side.
This is an atomic radius model. The atomic radius of a chemical element is a measure of the size of its atoms, usually the mean or typical distance from the center of the nucleus to the boundary of the surrounding cloud of electrons. Atomic size gradually decreases from left to right across a period of elements. This is because within a period or family of elements, all electrons are added to the same shell. However, at the same time, protons are being added to the nucleus, making it more positively charged. The effect of increasing proton number is greater than that of the increasing electron number. Therefore, there is a greater nuclear attraction. This means that the nucleus attracts the electrons more strongly, pulling the atom's shell closer to the nucleus. The valence electrons are held closer towards the nucleus of the atom. As a result, the atomic radius decreases.